Okay, here's an example from the textbook. In figures 5.15 and 5.16, they talk about a zero detector, a circuit whose output goes high when a zero is detected in a stream of ones. On the left you see the simple circuit diagram, and on the right you see the state transition diagram. Okay, let's take a look at some Verilog HDL, which implements the circuit we just described. This zero detector can be implemented in a number of ways, but some of the concepts shown in the textbook in this example are somewhat new to us. The first I want to point out is that here we have a parameter statement. This parameter statement indicates that we're declaring four variables, S0, S1, S2, and S3, which are actually constants. These are the four states shown in the previous state diagram. We have three always blocks, two of which are relatively small, the first and the third, and the middle, which is a bit longer. Now with the Mealy machine, we're worried about the input and the current state. The first always block, which I'll highlight here, really is mimicking the operation of a flip-flop. Always blocks run continuously. They are triggered in certain conditions. Well, in this always block, those conditions are when the clock has a positive edge transition or when the reset pin has a negative edge transition. When one of those things happen, this code is executed. And the purpose of this code is really to set the current state. The second always block is all about doing the combinational logic for the state transition. It has a simple case statement indicating the current state and then deciding which is the next state. And this mimics the state diagram we saw previously. Now, just like the previous always block, we have certain conditions which indicate when this will be triggered. In this case, when there are changes in either state or in the X input, this code will be executed. The third always block has the same conditions when state or the X input changes. We have another case statement here, but this is all about the output, the combinational logic which indicates the output. Here, if we're in state S0, the Y output is going to be 0. In any other state, the Y output is going to be the complement of the X input. So these three always blocks, which execute in parallel and are triggered using different conditions, implement the circuit we had seen in the previous diagrams. Now the test bench is a little bit different. The test bench, which will test this out for us, instantiates one of our Mealy zero detectors, the module we just looked at. It ends the simulation after 200 nanoseconds, and it has two initial blocks. The first sets the clock to 0 and then goes into an infinite loop where it complements the clock every 5 nanoseconds. The second initial block is a bit different. It has this word fork in it as well as the word join at the end. Now what this means is, unlike a simple initial block, which executes the statements within it one at a time in sequential order, a fork join initial block executes all of the statements in parallel. Now these delays, starting at 2 and then 87, 89, and so on, are relative to a common starting point, time equals 0. So the delays mean that they happen at different times, but in theory all of these statements are executing in parallel. Now this enables us to produce a waveform. The waveform you see here mimics that in figure 5.22 on page 226 of the course textbook. The peaks and valleys correspond to what you see in that diagram. Now on those pages, page 225 and 226, they do talk about some of the glitches inherent in this type of model relating to the sequence of events, and I encourage you to read that. But these waveforms help to give you a visual representation of how things change over time. Specifically, these four things are done by default: the clock, the reset pin, the X input, and the Y output. And from this, you can gain a measure of whether or not your circuit's working.